Alright, so let's go ahead and talk about how to use Hess's law. And for that, to that end, let's go ahead and use the problem shown here. And notice the overall goal of the problem is to find the enthalpy for this reaction of dinitrogen monoxide and nitrogen dioxide going to form nitrogen monoxide. Notice that this reaction is already balanced, as are the reactions up here. Here are a list of thermochemical equations, and what we're going to do is combine these equations in such a way as to get this overall equation. So what we want to look for is things that are in the equations above, but not in the equation down here, such as nitrogen and oxygen. And we also want to look at what's on the reactant side and the product side and try to find those in the equations above. So if you look up here, we see that nitrogen monoxide is here and here, and it should be on the product side of our reaction, which it is over here, but it's not here. Also, if you look for nitrogen dioxide is seen here. It's on the product side. It needs to be on the reactant side. And then here we have dinitrogen monoxide, which is shown here, and it's on the reactant side, but there's too many of them. We got two of them here, we only need one. So let's go ahead and figure out what we need to do to each of these equations in order to get the right thing on the right side in the right amounts. So first off, let's go ahead and write down this equation right here and see what it looks like. Okay, so N2 plus O2 goes to form 2NO. Well, we have NO on this side and NO on this side, so we probably won't need to reverse this equation, make the reactants products and the products reactants, but we might need to take half of this overall equation. Probably not, though. Let's look at the second one here. Here we have NO2. If we notice down here, we have NO2 also, but it's on the reactant side and it's half this amount. This is the only place in any of these equations where we find NO2, and so what we're going to do is write the reverse of this reaction and take 1/2 of it. So if we take 1/2, so divide each of these coefficients by 2 and reverse it, we see that we get NO2 goes to form, from here, we've got NO plus 1/2 O2, right? Because 1 divided by 2 is 1/2. So 1/2 O2. If we flip this, if we reverse the reaction, we're going to have to reverse the delta H. And if we take half of the reaction, we're going to have to take half of the delta H value. And so let me actually write down these delta H's too. So delta H for this top one is 180.7 kilojoules. Delta H for the second one equals, remember we reversed it, so we got to change the sign, positive, and let's put a positive there, 113.1 kilojoules, but we also took half of it, so we have to do the same thing to the enthalpy. So divide it by 2. Now for this final one, if we look down here, we see that we have NO2 on this side, and it is, N2O is nowhere found, or is found on this side of the reaction arrow, and again we have double the N2O that we need. We see that it's the only place where we have N2O in any of these equations, and so we're going to have to take 1/2 of this also. So divide by 2, divide by 2, divide by 2. So this one will end up being N2O goes to form N2 plus 1/2 O2. Now if you look right here, oh, and remember the delta H. So delta H equals negative 163.2 kilojoules over 2. So if you look right here, we have one O2 on the reactant side and 1/2 O2 here and 1/2 O2 here. So we can cancel the one total O2 with the 1/2s here, right? Because 1/2 plus 1/2 is 1 O2. Now if we look over here, we have N2, we have one N2, and here we have one N2. We got to cancel. Remember, we have to cancel on the reactant side on one side and the product side on the other side. And if you look at what we have left over, we have this, which is this, which is N2O, this, which is NO2, and then we have a 2 NO here and 1 NO here, so that goes to form 3 NO. And so we indeed, after we've added these equations together, we indeed do have the overall chemical equation that we want for our reaction here. And so we have done the Hess's law correctly. Now we just need to add up all the enthalpies. So if we get out our calculator, which is right there, we see that we have 180.7 plus 113.1 divided by 2 plus, or minus 163.2 divided by 2. And we end up with an overall, let me bring it back, 155.65 kilojoules. So an overall thing of overall reaction enthalpy of 100, what was it, 55, and we're going to round to that to that first decimal place. So 155.7 kilojoules of energy for this overall reaction.